Alrighty. The final is tomorrow. And since we have one day of no lecture before the final, I thought it would be a good day to go ahead and provide at least some sort of video or session that would act as a review session, right? I mean, if this was a normal in-person fall or spring semester, you would have recitation or lab, and the last day of recitation or the last day of lab would be review for the final, right? And so I think we deserve that in the summer semester as well. Summer semesters go by very quickly, but I wanted to push the material at least one day fast so that we did have a final day of no new material and just one day dedicated to nothing but review for the final. So what I'm going to be doing is going over the file titled Math 551 Final from Fall 17.pdf. This is one of the archived finals. You can tell it's from the Fall 17 semester. There's a handful of problems on here that are not relevant. And I struck those out on the document once you see the document. But I do want to go over all of those that are relevant, right? And so I think I cover, I don't know, 1, 2, 3, 4, 5, 6-ish problems, which is about the length of the final exam, right? The midterm was 6 problems with a bonus problem. You can expect the final to be of the same length. I haven't decided if I want to throw in a bonus problem or not yet, but I do know the length of the overall exam. So with that in mind, let's go ahead and start looking at some of the problems from this test that I think are good practice for the final. So the first one is number 3. And number 3 says, write the vector b, which is given by 1, 1, 1, as a linear combination of v1, which is given by 2, 1, negative 3, and v2, which is given by 1, 1, negative 1, if possible. Right? So it may not be possible. If it is possible, what do we need to do? We need to show, basically this is asking, this question is, do there exist, or does there exist A and B in the reals such that B is equal to A V1 plus B V2, question mark, right? That's what this problem is asking, is if you can write B as a linear combination of V1 and V2. Well, let's see if we can or not. And if we can, let's figure out what the values of A and B should be, right? So we want to set up B equals AV1 plus BV2. This is 1, 1, 1 is equal to A times V1, which was 2, 1, negative 3, plus B times V2, which was 1, 1, negative 1. We can simplify the arithmetic on the right-hand side to get, well, we'll scale both vectors and then add them together. And what we get is 2a plus b, a plus b, and then negative 3a minus b. And this is to be equal to 1, 1, 1. This implies we have the following system of equations. We have 2a plus b is equal to 1 for the first component. For the second component, we have a plus b is equal to 1. And then for the third component, we have negative 3a minus b is equal to 1. How do we solve this system, right? We solve this system by setting up an augmented matrix that represents the system, which is 2, 1, 1, 1, 1, 1, and then negative 3, negative 1, 1. Before we start, I'm going to flip row 1 and row 2 here. So let's exchange row 2 for row 1. It'll make the computation a little bit easier, right? So this is 1, 1, 1. And then we have 2, 1, 1, and -3, -1, 1. We have to put this into a reduced row echelon form, right? Because now the existence of A and B boils down to, does this system have a solution? Or this system, rather, right? So asking if such an A and B exist is asking if this system is consistent, right? So to see if this system is consistent, we need to convert this augmented matrix into its reduced row echelon form. You see, we can take row 2 and replace that with row 2 minus 2 row 1, and then row 3 can be replaced with row 3 plus row 1. If we do that, we get the matrix 1, 1, 1, and then we're going to have 0, and then 1 minus 2 is -1, 1 minus 2 is -1, and then we're going to have -3 plus, I'm sorry, that should not be row 1, that should be 3 row 1. So we have row 3 is -3 plus 3 is 0, and then we have -1 plus 3 is 2, and then we have 1 plus 3 is 4. We can take row 2 and replace that with -1 row 2, and then we can take row 3 and replace that with 1/2 row 3, and we'll get 1, 1, 1, and then 0, 1, 1, 0, 1, 2, right? Once we do that, you'll notice we can take row 3 and replace that with row 3 minus row 2. This gives us 1, 1, 1, 0, 1, 1. And then in the third row, we have 0 minus 0, 1 minus 1 is 0, 2 minus 1 is 1. Now, this isn't in reduced row echelon form, but it tells us everything we need to know. What is this bottom row, right? You want to keep in mind as you're going through the steps of putting an augmented matrix into reduced row echelon form, you want to keep in mind, what is this telling me algebraically? Or what is this telling me in terms of the system of equations? Well, this third equation now tells me that 0a plus 0b equals 1, which implies that 0 equals 1. But that's a contradiction, meaning, so we found a contradiction, thus, no such A, B in the reals exist for B to be equal to V, or I'm sorry, A V1 plus B V2. Maybe B was bad because we had the, yeah, that's, I kind of just caught that. That's really bad. Let's call this C. Let's call this vector C. Just, I mean, I think it was understood which one was a vector and which one was a scalar, but, you know, it's still bad practice. Blah, blah, blah. So C here. Right. And so this means no solution exists, right? We were asked to show that C is a linear combination of blah, blah, blah. If possible, we've shown that it's not possible, right? And it's the same process. Cool. So that's how we show that something is or is not a linear combination of other elements, right? We set up the linear combination. It has a corresponding system of equations, and then we see if that system is consistent or not. If it's consistent, then the solution to that system is the scalars that make C, right? It makes whatever vector a linear combination of the others. And then if it's not consistent, like we've seen here, well, then we know no such linear combination exists. What else would this be saying? This would be saying, by the way, I'll erase up here, just for some understanding here. The answer to 3 tells us that C is not an element of the span of V1 and V2, right? Because we've shown that C is not a linear combination of v1 and v2. Because remember, what is the span as a set? This is the set of vectors v such that there exist a and b in R such that v equals a v1 plus b v2, right? That's by definition what the span is. It's the set of all vectors that can be obtained as a linear combination of the original vectors. And so showing, right, I'm just saying, like, if on the final or something, you were to ask to make a conclusion about the spanning set of v1 and v2 or something, well, you would be able to say that C is not an element of the spanning set, right, for v1 and v2. Okay, let's look at the next one. Let's look at number 4. We have a set S, which is defined as a spanning set. This is the span of the vectors 1, -1, 1, 2, 1, -1, 1, 0, 0, 1, 1, 1. Okay, and it wants us to find a basis for S. Okay, and so it wants us to find a basis for S. Well, we have a spanning set, but of this spanning set, how do we know which of them are linearly dependent on the others, right? Because a basis, remember, by definition, a basis is a linearly independent spanning set. And so we have a spanning set here. We just don't know if it's linearly independent or not, right? And so to get a basis, we would need to pluck out all of the elements that are linearly dependent. So how do we do that? We set up the augmented matrix that consists of, the first entry of the spanning set is the first column. The second is the second, right? And so we're setting up this matrix that's really, we're augmenting all of the spanning, or all the elements of the spanning set here, or the elements that we're taking the span of, rather, right? We augment those into a matrix where the columns are these elements. And now you put this into reduced row echelon form. So let's put this into reduced row echelon form. Well, you can see here, we have row 2 would be row 2 plus row 1, and then row 3 would be row 3 minus row 1. That gives us, well, we have 1, 2, 1, 1 because the first row didn't change. Then we have -1 plus 1 is 0, 1 plus 2 is 3, 0 plus 1 is 1, 1 plus 1 is 2. And then we have 1 minus 1 is 0, -1 minus 2 is -3, 0 minus 1 is -1, and then 1 minus 1 is 0, right? What can we do from here, right? Well, then we can say row 1, or I'm sorry, we can say row 3 is equal to row 3 plus row 2. And what will we get there? In that case, well, row 1 is the same still, 0, 1, 0, no, 1, 2, 1, 1, getting ahead of myself, 0, 3, 1, 2, because we didn't change either of the first two rows. And then we have 0 plus 0, we have -3 plus 3, and then we have -1 plus -1, and 0 plus 2, right? We can do a little bit of simplification here. Let's say row 2 is equal to row 2 over 3, and then row 3 is equal to row 3 over 2. This gives us 1, 2, 1, 1, 0, 3, 1, 2. Well, what am I doing? Not doing any of the operations. 0, 1, 1/3, 2/3, and then 0, 0, 0, 1. Right? To get this into reduced row echelon form, we need to get rid of this element and this element and this element, right? So how can we do that? Well, let's get rid of the 2 first. Let's say row 1 is equal to row 1 minus 2 row 2. That gives us 1 minus 0 is 1. 2 minus 2 is 0. 1 minus 2/3 is 1/3. 1 minus 2/3 is 1/3. That should be negative because it would be 1 minus 4/3, right? So that should be -1/3. And then we have 0, 1, 1/3, 2/3, 0, 0, 0, 1. You can see pretty easily two operations give you, right? These are all zeros. So you just multiply by the appropriate constant, add it to row 1 and row 2, and then you'll get 1, 0, 1/3, 0, 0, 1, 1/3, 0, 0, 0, 0, 1. Now, this is in reduced row echelon form. How does the reduced row echelon form help us determine the subset of these vectors which are linearly independent? Well, you look at every column that has a pivot spot or a pivot entry, right? Or you look at the pivot columns. The pivot columns of the reduced row echelon form are 1, 2, and 4. This implies the linearly independent vectors are v sub 1, v sub 2, and v sub 4, where if you come back to the original problem, if we named this one v1, v2, v3, v4, right? Pretty nice way of seeing what subset of these is linearly independent. So which means our basis, and let's say like b sub s, right? The basis for s is going to be the vectors v1, v2, v4, which is 1, negative 1, 1. And I'm just copying what these were from the original problem, right? 2, 1, negative 1. And then 1, 1, 1. So here's our basis. What does this mean? This implies that the dimension of S is what? The number of basis elements is equal to the dimension of the space, right? So that means the dimension of S is 3. It's a three-dimensional vector space. What it also wants us to do in this problem is you'll notice the one vector that's linearly dependent was V3. Well, if it's linearly dependent, that means we should be able to write V3 as a linear combination of V1, V2, and V4. And the problem asks us to do that. So find A, B, C, and R such that V3 equals A V1 plus B V2 plus C V4, right? Not 3. That was muscle memory. C V4. Cool. Let's look here. Well, so this would be V3 is 1, 0, 0 equals A, and then V1 was 1, negative 1, 1. B what, or I'm sorry, B times V2, which V2 was 2, 1, negative 1 plus C, and V4 was 1, 1, 1. So normally what you would do, right, to solve for A, B, and C, and this is what you should do if you can't see the values for A, B, and C by inspection, what you should do is set up, again, like we did in the previous problem, you set up the augmented matrix, right? 1, negative 1, 1, 2, 1, negative 1, 1, 1, 1, and then 1, 0, 0. And you work down to the reduced row echelon form, right? Whatever that is. And then that will tell you the values for A, B, and C because you've solved this system of equations, right? Here, I notice one thing. I notice that I want zeros in entries 2 and 3, right? And I so happen that V1 and V2 are equal but opposite in their components, right? So, well, for components 2 and components 3. And so I want to just look at those. Let's just look at C being equal to 0. Well, then I need, right, if I add, say if I just let A equal 1 and B equal 1, then I would get the vector 3, 0, 0, right? But I want the vector 1, 0, 0. So that means I should take A is 1/3, which is also B. Well, then 1, 0, 0 is 1/3 times 1, negative 1, 1 plus, 1/3 times 2, 1, -1, which is going to be 1/3 plus 2/3, and then -1/3 plus 1/3, and then 1/3 minus 1/3, which is 1, 0, 0 as desired. So we found the coefficients or the scalars that make V3 a linear combination of V1, V2, and V4. Okay. I think I'll probably, well, let's do one more problem on this video, and then in the next one we'll look at the rest of the problems. So let's look at the next one here. We have U, which is given as the following set. It's a set of vectors x1, x2, x3, x4 in R4 such that x1 plus x2 minus x3 plus 2x4 is equal to 0, and negative x1 minus x2 minus x3 minus 4x4 is equal to 0. And we want to show that U is a subspace of R4, and we also want to find a basis for U. Okay, so what do we have to do here? We have to show that U is a subspace, and to show that something is a subspace, let's recall, let's say V, or rather W in V is a subspace if for all x and y an element of W, that implies AX plus BY is also an element of W for all scalars AB, right? And so this should also include the 0 vector. You can see, like for U, if you let x1 through x4 all be 0, then that criteria is satisfied. So 0 is an element of U. We don't really need to worry about that. But we do need to verify this criteria for the given subset of R4 here, right? So let's do that. To do that, we need to set up the following thing. We need for two elements, x, y, right? So whoops. Let's consider x and y elements of U, right? And let's give them some names. So x is x1, x2, x3, x4 here. And then y, will that be similarly, y is, y1, y2, y3, y4. Now, let's look at ax plus by. We need to show that this is an element of U for any combination ax plus by here, right? So what is this equal to? This is equal to A times x1, x2, x3, x4 plus B times y1, y2, y3, y4. Let's combine these vectors and we get ax1 plus by1, ax2 plus by2, ax3 plus by3, and ax4 plus by4. Now, what do we have to show, right? Let's give these some names really quickly. Let's call this Z1. So let's say Z, which is equal to ax plus by. This is Z1, Z2, Z3, and Z4. What does it mean? So how to show that Z is an element of u, question mark, right? Where z is, again, ax plus by. How do we show this? Well, we need to show, so want to show that the components z1 through z4 satisfy the criteria for being an element of u, right? Namely, we need to show the elements z1 through z4 satisfy these two equations. Let's start with the first one. The first one, we want to show that z1 plus z2 minus z3 plus 2z4 is equal to 0. So how can we show that? Well, let's just compute the left-hand side, right? z1 plus z2 minus z3 plus 2z4. This is equal to, let's sub in what z1 is, right? z1 is ax1 plus by1. z2 is ax2 plus by2 minus z3. So ax3 plus by3 plus 2z4 is ax4 plus by4. What do we have? Well, let's group everything that has an a, right? Everything that has a factor of a in it and everything that has a factor of b in it. So we can see for the factor of a, we have ax1 plus ax2 minus ax3 plus 2ax4. So this is equal to ax1 plus ax2 minus ax3 plus 2ax4. And we can do the same thing for the y terms, right? We have by1 plus by2 minus by3 plus 2by4. So this is plus by1 plus by2 minus by3 plus 2by4. Let's factor out the a from the first four terms. So that's a times x1 plus x2 minus x3 plus 2x4, and then plus, we factor out a b, which is y1 plus y2 minus y3 plus 2y4. However, x and y belong to the subset U. And if x and y belong to the subset U, this is equal to a times 0 plus b times 0, right? This whole thing being equal to 0 is since x is an element of U, and this whole thing being equal to 0 is since y is an element of U. And so this is equal to 0. And so this means we've satisfied the first equation. We need to do the same thing for the second equation, right? We need to show that negative z1 minus z2 minus z3 minus 4z4 is equal to 0, right? Well, to show that that's equal to 0, let's go through the similar process here. Let's compute what this is. This is minus ax1 plus by1, and you probably get the idea by now. ax2 plus by2 minus ax3 plus by3 minus 4ax4 plus by4. We do grouping in a similar manner, right? This was equal to, by the way. And so we're going to get, it looks like a times negative x1 minus x2 minus x3 minus 4x4 plus b times negative y1 minus y2 minus y3 minus 4y4. This is equal to a times 0 plus b times 0, which is 0, which implies now that z is an element of U, where z was ax plus by. Therefore, U is a subspace of R4, right? Because what did we do? We had to show that for any two elements that satisfy, where'd we go? For any two elements that satisfy these equations, we have that any linear combination also satisfies these equations. That's exactly what we've shown, right? We've showed that for the first equation here. And then we've shown that for the second equation here. Great. So this is a subspace. Now we need to find a basis. How do you find a basis of this? Right? Well, finding a basis means you need to find a linearly independent spanning set. And when you're looking for a basis, you always go to the restrictions, right? What are the restrictions of elements here is defined based on these two equations here, right? The first one, well, the second one and the first one here. So what do we need to do? We need to solve this system of equations to figure out what types of vectors x1 through x4 is, right? And so really, to find a basis, well, what we're doing is we need to understand or look at the restrictions. And the restrictions are namely x1 plus x2 minus x3 plus 2x4 is equal to 0, and negative x1 minus x2 minus x3 minus 4x4 is equal to 0. That means we can solve the following system of equations. 1, 1, negative 1, 2, 0. This is going to be a 2 by 5 matrix, actually. Negative 1, negative 1, negative 1, negative 4, 0. Well, if we take, right, and now we're trying to solve the system of equations. So let's take row 2 is equal to row 2 plus row 1. What does that get us? 1, 1, negative 1, 2, 0. And then we have negative 1 plus 1 is 0. Negative 1 plus 1 is 0. Negative 1 plus negative 1 is negative 2. Negative 4 plus 2 is negative 2. And 0 plus 0 is 0. We can divide through by negative 2 to row 2, and we will get the following. Let's see, where am I? We should get 1, 1. Did I mess a sign up there? Negative 1 plus, no, I think I'm good, right? Negative 1 plus negative 1 should be negative 2, and then negative 4 plus 2 should also be, yeah, we're good, we're good. So this is 1, 1, negative 1, 2, 0, and then 0, 0, 1, 1, 0. We can write then row 1, right? This isn't in reduced row echelon form yet. To be in reduced row echelon form, we have to take row 1 and say row 1 is equal to row 1 plus row 2. That should give us, well, row 2 was unchanged, right? And then row 1, we'd have 1 plus 0 is 1, 1 plus 0 is 1, and then negative 1 plus 1 is 0, and then 2 plus 2 plus 1 is 3, and then 0. And so what does this mean, right? Now this means x1 plus x2 plus 3x4 is equal to 0, and this means x3 plus x4 is equal to 0. This means we have the following. Let's give, well, we have x1 is going to be equal to, sorry, x3 is going to be equal to negative x4, and x4 is equal to x4. So let's give this a parameter t, and then we also have this x2 here, right? x2 depends on nothing else, so let's say x2 is equal to s. So with the parameters x4 equals t and s2 equals s, we have the following, right? We have x1 is equal to, and then it's going to be negative s minus 3t, right? And then we have x2 is equal to s, x3 is equal to negative t, and x4 is equal to t, right? Because here you subtract the x4 over, you get x3 is equal to negative x4. And so what does this mean, right? Well, then this means x1, x2, x3, x4. This means, so all vectors in U are of the form negative, not negative, S times the vector -1, 1, 0, 0 plus T times -3, 0, -1, 1. Right? And so it's very easy to verify that these two vectors are linearly independent. To show that they're linearly independent, well, you know, it's not too hard. And what we do then is we understand that this is also a spanning set. So this implies that the basis or a basis for U is given by -1, 1, 0, 0, -3, 0, -1, 1. And this is our basis for U. Okay. So, and maybe I'll leave this for you guys. So check that, I'll call this V1 and this V2. Check that V1 and V2 are linearly independent, right? Really, all you would need to do is set up -1, 1, 0, 0, -3, 0, -1, 1. Show that both columns are pivot columns, and then you're done. So, right? And for just two vectors, you could see this as soon as you realize that one isn't a linear combination, or not a linear combination, but like you can see right away that one of these vectors is not just scaling, right? You don't obtain, say, V2 by scaling V1 or vice versa, right? So you can almost just tell that these are linearly independent by inspection. So maybe I'll just not even leave that as a check. You can just kind of say in words, right, that, well, there does not exist A in R such that A times -1, 1, 0, 0 is equal to -3, 0, -1, 1, right? Because the bottom would imply that 0 equals 1, so you're done. Okay. So this was a problem, a pretty good problem finding a basis for a given subspace of R4. Next, what we're going to do is let's do a few problems that deal with the spectral theory, right? Eigenvalues, eigenvectors, orthogonality, diagonalization, things like that. So that's what we're going to do from here. All right, I decided to just make this one video, I think. So I'll kind of just splice these together, and then I'll just post one video for the final exam review. So what are we doing next, right? The next problem we're going to look at is problem number 9 from the same final here from fall 17. And we want to find eigenvalues and vectors of the matrix A, which is given by 101, -1, 1, -1, and 1, 0, 1. Okay. To find the eigenvalues, well, to find the eigenvectors, you have to find the eigenvalues, right? But how do we find eigenvalues? Eigenvalues, lambda, are solutions to the characteristic equation, which is the determinant of lambda I minus A is equal to 0, right? And remember, let's take a step back. What are eigenvalues and eigenvectors? Those are scalars, lambda, and vectors x, such that ax equals lambda x, right? These are your eigenvalues and eigenvectors. So how do we find lambda, right? Well, we find lambda by finding the roots to the characteristic polynomial. And that's exactly what we're going to do. So if A is that matrix, then we have, let's calculate lambda I minus A. This is lambda times 1, 1, 1, 0, 0, 0, 0, 0, 0, minus a, which is 101, negative 1, 1, negative 1, 1, 0, 1, which is, looks like it's going to be lambda minus 1, 0, negative 1, pardon me, 0, no, positive 1. Positive 1, lambda minus 1, positive 1, and then negative 1, 0, lambda minus 1. Let me double check with what I got to make sure I'm not crazy. All right, we're good. So what we're doing is we're finding the determinant of the matrix, lambda minus 1, 0, negative 1, 1, lambda minus 1, 1, negative 1, 0, lambda minus 1, right? Now, what's the determinant of this matrix? That's lambda minus 1 times, and I'll do this the long way here. It's going to be lambda minus 1 times lambda minus 1 minus 0 minus 0 times, well, let's just write this out for the sake of practice, right? We understand that this whole term is going to vanish, but this would be 1 times lambda minus 1 minus 1 times negative 1, and then plus negative 1 times 0 minus a negative, so plus lambda minus 1. This simplifies to lambda minus 1 cubed minus lambda minus 1, right? Because it was plus lambda minus 1, but we have this negative 1 here, so that's minus lambda minus 1. So this is our characteristic polynomial. To find the roots of this, we need to set lambda minus 1 cubed minus lambda minus 1 equal to 0. Well, to do this, let's factor out a lambda minus 1 on the left-hand side, right? So that's lambda minus 1 times lambda minus 1 quantity squared minus 1 equals 0, which is lambda minus 1 times lambda squared minus 2 lambda plus 1 minus 1 equals 0, which is lambda minus 1 times lambda squared minus 2 lambda equals 0, which is lambda times lambda minus 1 times lambda minus 2 equals 0, which means we have 3 distinct eigenvalues. Lambda 1 equals 0, lambda 1, or lambda 2 equals 1, and lambda 3 equals 2. So we found the eigenvalues. Next, we need to find the corresponding eigenvectors, right? So how do we find the corresponding eigenvectors? Well, if you'll remember, we have eigenvectors first off, they're non-zero. You can never get a zero eigenvector. Satisfy AX equals lambda X, right? Or if you would like, this is the same as lambda I minus A times X equals 0, right? Either one, you can use either one however you want to solve this. For lambda 1 equals 0, I'm going to use the first equation here, right? The first equation says that A, which was 1, 0, 1, negative 1, 1, negative 1, 1, 0, 1, times X, which we'll call X1, X2, X3, this should be equal to 0, right? This should be equal to 0 times X1, X2, X3, which is really just the 0 vector. So what we get is that this, and I'll just write it here, this should be equal to 0, 0, 0. This gives us a system of equations, right? This gives us a homogeneous system of equations given by Well, let's write out what they are. Or let's write the augmented matrix for them. So this is 1, 0, 1, 0, and then -1, 1, -1, 0, 1, 0, 1, 0. You can put this into reduced row echelon form in one step here. If row 2 is equal to row 2 plus row 1, and then row 3 is equal to row 3 minus row 1, then you're getting 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, right? And so what does this say? This says x1 plus x3 is equal to 0 and x2 is equal to 0, i.e. x1, x2, x3 is of the form, if we give x3, let's say x3 is equal to t, this is equal to -t, 0, t, and so we can find just the basic eigenvector by taking t equals to 1, and we get x1 is equal to -1, 0, 1. And so this was for lambda 1 equals 0. We had the basic eigenvector -1, 0, 1, right? And so we need to do this for the remaining eigenvectors. So let's look at lambda 2 is equal to 1, right? What is this saying? This is saying that, well, right, we're looking at lambda I minus a times x equals 0. What is lambda I minus a? Well, lambda is equal to 1, so this is really I minus a times x is equal to 0. We know what I minus a is. That's going to be, you just flip the sign, so we have 0 down the diagonal, right? Or if you'd like, let's come back to where we calculated lambda I minus a. Plug in lambda equals 1 here, right? Lambda, that gives you 0 along the diagonal, and then you just copy the rest down. So I'll just copy the rest of what we got there. That should be, let me go back here. That should be 0, -1, 1, 1, -1, 0 times x1, x2, x3 is equal to 0, 0, 0. That gives us the following system. And honestly, I don't think we need to do anything here, really, because the top equation tells us that -x1 is equal to 0. The second equation tells us that x1 plus x3 is equal to 0. And the bottom equation tells us that, well, again, -x1 is equal to 0. x2 is free, so x2 we'll just call t. This implies that x3 is also equal to 0, and so for x2, these are vectors of the form x1, x2, x3, which looks like 0, t, 0, i.e. we can take a basic eigenvector of t equals 1 to get, so for lambda 1, or excuse me, lambda 2 equals 1, we get the eigenvector 0, 1, 0, right? Now let's do the same thing, but for lambda equals 2. So lambda 3 equals 2 here. Then we're setting up, what is lambda I? So we have 2I minus a times x equals 0. Well, this is going to be 2I minus a is going to be what? That's going to be 1. Well, it's going to be the same thing, but with 1s along the diagonal instead of 0s, right? Because you're plugging in 2 for lambda. So 1, 0, -1, 1, 1, 1, -1, 0, 1 times x1, x2, x3 equals 0 here. So let's see what this has. I think we can avoid solving a system of equations here as well, or putting it into a matrix. So this says The top one says x1 minus x3 is equal to 0. The second one says x1 plus x2 plus x3 is equal to 0. x1 plus x2 plus x3 is equal to 0. And then the last one says negative x1 plus x3 is equal to 0. So both of these just tell us that x1 equals x3. Let's give that a parameter t, okay? And then the middle equation tells us that x2 is equal to negative 2x3. And so for vectors x3, we're going to have, it looks like we'll have t negative 2t t, which this is for t and r. That means we can take a basic eigenvector for lambda 3 equals 2. We can get the eigenvector 1, negative 2, 1. And let me double check and make sure that's what I got. That is what I got. Great. So we have now found all eigenvalues and the corresponding eigenvectors. Okay. I do want to say one thing here. I want to, here's kind of a remember or recall. While we're on the topic of eigenvalues and eigenvectors, remember, A is diagonalizable if and only if P, right? Well, remember, what does diagonalizable mean? Diagonalizable means there exists P invertible and diagonal matrix D such that D is equal to like P inverse A P, right? But so that's the definition, is if you can find this invertible matrix such that P inverse AP is similar, or such that A is similar to a diagonal matrix, right? So, but remember, you can use eigenvalues and eigenvectors. A is diagonalizable if and only if P, which is given by the column vectors x1, x2 through xn, is invertible, right? i.e. the determinant of P is not 0. And if that's the case, then you know A is diagonalizable, and you can find the matrix, the diagonal matrix that it's similar to very simply. Then D is the diagonal matrix lambda 1 through lambda n with zeros everywhere else, right? So I just wanted to remind everyone of that. It may or may not show up on the exam, but diagonalizability, if you know what you're doing, that's just like, then that question, like, say if I were to be like, find or prove that A is diagonalizable and then find the diagonal matrix that it's similar to, or something like this, right? Well, then all you have to do is find eigenvalues and eigenvectors. And so it would be this process that we've just done here. Well, and then after that, you just have to take a determinant. And then if it's non-zero, then your work is done, right? And so that's why I'm not doing a diagonalizable example, is because if you know this theorem, you just see previous example for how to solve it, right? Because you just need to find eigenvalues and eigenvectors. Okay. Lastly, let's do the bonus problem here. This is the bonus problem. And it says, consider real numbers x, y, z, and the matrix B given by 0, 0, x, 0, y, 0, 1, 0, z. And here's the question, is what values of x, y, z make B an orthogonal matrix? Right? And what does it mean that B is orthogonal? It means the column vectors form an orthogonal set, right? So orthogonal, this means the dot product of any two column vectors is equal to 0. Let's say any two distinct, right? Because the dot product of a vector with itself is never 0 unless you're taking the dot product of the 0 vector, right? So what does this mean? Well, for B to be orthogonal, so B, which is 0, 0, x, 0, y, 0, 1, 0, z, we need the dot product of any pair to be 0. So that means we need 0, 0, x dot 0, y, 0. We need this to be equal to 0. We need 0, 0, x dot 1, 0, z to be equal to 0. And we also need 0, y, 0 dot 1, 0, z to be equal to 0. The dot product is commutative, so this takes care of all pairs here, right? This is 3 choose 2 number of possibilities. Now, you'll notice the first equation is true for all x and y in R. So the first equation gives us no restriction, right? Every time you're going to have 0 times 0 plus 0 times y plus x times 0 equals 0. Well, it doesn't matter what values x and y are. Here, this implies that you necessarily need the product of x and z to be equal to 0. So that's a restriction, right? We also need, well, from the third one, we again get no restriction. This is true for all y, z, and r, because you're going to get 1 times 0 plus 0 times y plus 0 times z is 0. That's 0 plus 0 plus 0, no matter what values for y and z you choose. So B is orthogonal when x, z equals 0. Well, what does this mean? This implies that x equals 0 or z equals 0. And this is an inclusive or, right? There's like an or that means one or the other, and there's an or that means at least one, right? And this is an inclusive or. Or can also mean both, right? So what do we have here, right? Then what does this mean? Well, if x is 0, let's exhaust all of our possibilities. If x is 0, then the matrix is going to look like 0, 0, 0, 0, y, 0, 1, 0, z. These are orthogonal. If z is 0, you're going to have 0, 0, x, 0, y, 0, 1, 0, 0. And then if both of them are 0, you're going to have 0, 0, 0, 0, y, 0, 1, 0, 0. This is your family of orthogonal matrices of the form given by B, right? Notice the only orthogonal matrices with a non-zero column is the middle one here. These are the only orthogonal matrices with non-zero columns, right? So there you go. So this would be the solution to the bonus problem. And what you're looking at, again, when you're looking for something orthogonal, an orthogonal matrix is one that the dot product of any pair of columns is 0, right? Or you have that the set of column vectors is an orthogonal set. And remember, just for review here, orthonormal, this is equal to orthogonal plus column vectors have unit length or magnitude 1, right? So just for review. Okay, so I think that wraps up the practice for the final. Remember, these practice exams don't cover anything over the material that we've talked about in chapter 9, which is kind of linear algebra for an arbitrary vector space, right? And so something like this may or may not pop up on the homework. It won't be too much of a curveball I promise. If it is, then it'll be a fair curveball. So it's easy for me to say something isn't a curveball and then a student to say that it actually was a curveball. So if something like this shows up, it will be very similar to what this last homework, this optional homework was like in practice. So if you have any questions as we approach the final, please do not hesitate to send me an email. I would rather a student have questions before the final than during the final, right? So good luck studying, and I've had a great time teaching you this semester.